August 29, 1944, when 3 B-29s changed history. Vladivostok, Soviet Far East. 3 Boeing B-29 Superfortresses sat on a Soviet military airfield interned after emergency landings following bombing missions against Japanese targets in Manchuria. The crews, 44 American airmen, would eventually be repatriated through Iran. The aircraft would not. Joseph Stalin personally ordered the bombers held, not as bargaining chips, not as trophies, but as blueprints for reverse engineering the most technologically advanced aircraft in the world. Soviet engineers descended on the 3 B-29s like archaeologists excavating alien artifacts. They measured every dimension, photographed every component, drew diagrams of every system. What they discovered shocked them into understanding how far behind Soviet aviation had fallen. Each B-29 contained 55,000 separate parts. 600,000 rivets held those parts together. More rivets than the entire fuselage of a Tupolev SB-2 medium bomber. The electrical system alone used 9 miles of wiring. The pressurization system employed technologies Soviet engineers had never seen implemented in aircraft. The complexity wasn't just impressive, it was terrifying. This single aircraft represented industrial and technological capacity Soviet engineers struggled to comprehend. Each B-29 cost $639,188 in 1945 dollars, or approximately $10.5 million today. The entire B-29 program had cost $3 billion, more than the Manhattan Project that created the atomic bomb. Stalin ordered exact copies built. The resulting Tupolev T-4 program consumed 900 factories, employed tens of thousands of engineers, and took 3 full years to produce the first aircraft. Soviet industry had to develop entirely new manufacturing processes, create new alloys, and train workers in techniques they'd never encountered. And this was with 3 complete examples to study. Soviet engineers could disassemble every component, measure it precisely, and copy it exactly. Yet even with this overwhelming advantage, replication took 3 years of intensive industrial effort. Japan never captured an intact B-29. Japanese engineers studied wreckage from crashed bombers and analyzed components salvaged from shot-down aircraft. What they learned told them the war was already lost, not through any single decisive battle, but through industrial capacity Japan couldn't hope to match. This is the story of the B-29 Superfortress, the most complex weapon of World War II, more expensive than the atomic bomb it carried, built by manufacturers who transformed aircraft production from craft to industry through systematic application of mass production principles that stunned enemies and amazed allies. The B-29's story began not with a design, but with a vision. A bomber capable of striking Japan from bases so distant the Japanese fighters couldn't reach them. In 1939, Europe was descending into war, but America remained neutral. Still, military planners understood that modern warfare demanded long-range striking power. The B-17 Flying Fortress, America's premier heavy bomber, had range limitations. Fully loaded, B-17s could strike targets approximately 2,000 miles round trip. That was adequate for European operations, but insufficient for Pacific distances. Major General Henry H. Hap Arnold, commanding the Army Air Corps, wanted a bomber that could fly 5,333 miles, carrying a 2,000-pound bomb load at speeds exceeding 400 miles per hour. The specifications seemed impossible with 1939 technology. No aircraft of such range existed. No engines produced enough power efficiently enough to achieve those numbers. The aerodynamics, structures, and systems required hadn't been invented yet. Arnold didn't care. He believed American engineering could solve any technical problem if sufficient resources and urgency were applied. In November 1939, he issued formal requirements to Boeing, Consolidated, Douglas, and Lockheed. Design a very long-range bomber meeting these specifications. Boeing's response was the Model 345, a massive four-engine bomber incorporating technologies that existed only as theories or laboratory experiments: pressurized cabin, remote-controlled gun turrets, analog fire control computers, and tricycle landing gear. The Air Corps ordered 2 B-29 prototypes in August 1940, 14 months before Pearl Harbor. By May 1941, a production order for 250 aircraft had been issued despite no prototypes flying yet. The unprecedented decision reflected Arnold's conviction that this bomber would be essential to defeating Japan. But nobody, not even Boeing's optimistic engineers, fully understood what they'd committed to building. The first B-29 prototype took its maiden flight on September 21, 1942, from Boeing Field in Seattle. Test pilot Edmund T. Allen, Boeing's chief test pilot, spent 75 minutes airborne evaluating handling characteristics. His assessment was cautiously optimistic. The aircraft flew, the pressurization worked, the controls responded adequately despite the bomber's massive size. But problems were immediately apparent: engine overheating, fuel system leaks, and electrical issues that would require extensive debugging. 4 months later, February 18, 1943, Allen was conducting the 5th test flight of the second B-29 when fire erupted in the No. 1 engine nacelle. Fuel lines ruptured, flames spread to the wing structure. Allen tried to return to Boeing Field, but the fire spread too fast. The bomber crashed into the Fry meat packing plant 2 miles north of the airport, killing Allen, his 9 crew members, and 20 workers in the building. The crash investigation revealed systematic problems with the Wright R-3350 engine, the complex 18-cylinder radial that powered all 4 propellers. The engines ran dangerously hot. Fuel lines routed through areas where heat caused metal fatigue and cracking. The cowl flaps designed to cool engines proved inadequate. Engine problems would plague B-29 operations throughout the war. The R-3350 was powerful, 2,200 horsepower, but temperamental. Mechanics called it the right wrong, and crews dreaded engine failures that occurred with alarming frequency. Over 400 B-29s would be lost to engine fires, mechanical failures, and related accidents, more than were lost to Japanese defensive action. But Arnold refused to delay production. The bomber was desperately needed. Engine issues would be solved in parallel with production. Modifications would be incorporated as aircraft rolled off assembly lines. The alternative, waiting until every problem was fixed, would delay deployment by years. The decision was characteristically American. Build it now, fix it later, overwhelm problems through sheer volume of effort.
Manufacturing the B-29 required building an entirely new industrial infrastructure. Boeing's existing plants were overwhelmed producing B-17s. The B-29 was too large, too complex, and too different to fit into existing production facilities. 4 massive new factories would be constructed specifically for B-29 production: Boeing Wichita, Kansas, Boeing Renton, Washington, Bell Marietta, Georgia, and Martin, Omaha, Nebraska. Beyond these 4 main assembly plants, thousands of subcontractors produced components. Wright Aeronautical built engines. Hamilton Standard made propellers. Suppliers across America manufactured the 55,000 parts that comprised each bomber. The scale was unprecedented. The B-29 program eventually involved over 60 primary contractors and 1,500 subcontractors. Peak employment across all facilities exceeded 90,000 workers directly manufacturing B-29s, with another 250,000 working for suppliers. Understanding why the B-29 was so expensive and complex requires examining what made it revolutionary: pressurized cabin. The B-29 was the first production bomber with fully pressurized crew compartments. Forward compartment, nose and cockpit, and rear compartment, waist gunner and photographer positions, maintained cabin pressure equivalent to 8,000 feet altitude while flying at 30,000 feet. This allowed crews to work without oxygen masks or bulky high-altitude clothing, dramatically reducing fatigue on missions lasting 12 to 16 hours. The pressurization system required airtight fuselage sections with pressure-sealed doors, cabin superchargers drawing compressed air from engines, pressure regulation valves maintaining consistent cabin altitude, pressure-tight electrical and control cable penetrations, and a 34-foot pressurized tunnel connecting forward and aft compartments. Remote gun turrets. 5 turret positions, 4 remote, 1 manned tail turret, housed 10 .50 caliber machine guns. The central fire control system, developed by General Electric, allowed any gunner to control multiple turrets. Sighting stations used analog computers calculating lead angles based on target speed, range, altitude, and air temperature. The system components included electric motors positioning turrets with precision, analog computers, electromechanical devices using gears and servos, sighting stations with integrated optics and computing mechanisms, ammunition feed systems delivering .50 cal rounds to multiple turrets, and electrical control systems coordinating fire from different stations. 4 Wright RD-3350 engines. Each 18-cylinder radial produced 2,200 horsepower, driving 16-foot 6-inch Hamilton Standard propellers. Turbo superchargers maintained power at altitude. Engine management required complex fuel injection systems, oil cooling systems with individual radiators, exhaust-driven turbo superchargers, engine fire suppression systems, and vibration dampers and mounting systems absorbing radial engine torque. Tricycle landing gear. The B-29 pioneered tricycle landing gear for heavy bombers, nose wheel plus main gear. This improved visibility during taxi, takeoff, and landing, but it required hydraulic systems operating multiple gear mechanisms, precise weight distribution calculations, reinforced nose structure supporting landing loads, and complex retraction mechanisms fitting gear into confined spaces. Electrical systems. 9 miles of wiring connected hundreds of electrical components. The B-29 required electricity for gun turret operation and fire control computers, hydraulic pump motors for flight controls and landing gear, cabin pressurization controls, navigation and communication equipment, engine controls and monitoring instruments, and bomb bay doors and weapons release systems. Assembly challenge. These systems didn't exist as modular units that could be installed separately. Everything interconnected. Pressurization affected electrical penetrations. Gun turrets required structural reinforcements. Engines interfaced with fuel, electrical, and control systems. Every installation required coordination across multiple trades and disciplines. Building a B-29 required 157,000 man-hours for early production aircraft, 20,000 man-hours after production optimization by 1945, over 1,500 skilled workers involved in each bomber, 3 to 4 months construction time initially, 1 to 2 weeks assembly time at peak efficiency.
Boeing Wichita faced challenges that seemed insurmountable when B-29 production began in 1943. The facility was still under construction when the first components arrived. Workers who had spent careers building simple PT-13 biplane trainers now faced assembling the world's most complex bomber. Engineering changes arrived constantly, sometimes daily, as test flights revealed problems requiring immediate fixes. The first Wichita-built B-29 was accepted by the Army Air Forces on March 3, 1944, serial number 426205. It had taken months of painful learning, thousands of man-hours debugging systems, and extensive rework fixing problems discovered during assembly. But Boeing applied automotive assembly line principles systematically. Modular subassembly. Rather than building bombers piece by piece on final assembly jigs, Wichita broke construction into major modules. Wing sections built separately, complete with fuel tanks and landing gear. Fuselage sections assembled with pressurization systems in internal equipment. Tail section completed as a unit. Bomb bay fabricated with structural components. These modules converged at final assembly where they were joined, tested, and completed. Moving assembly line. Rather than keeping aircraft stationary while workers moved, Wichita's line moved aircraft through sequential stations. Each station performed specific tasks. As soon as work completed at one station, the aircraft moved to the next. Workers became specialists at their station's tasks rather than generalists. Continuous improvement. Engineers tracked man-hours per station, identifying bottlenecks. Training improved skills. Tool improvements reduced installation time. By late 1944, Wichita had reduced construction time from 157,000 man-hours to under 20,000, an 87% reduction through systematic process refinement. Production volume. In 1944, Wichita averaged 3 to 4 B-29s weekly. Peak was 4.2 B-29s daily on June 5, 1945. Total was 1,644 B-29s plus 125 built as spare parts kits. At peak, Wichita employed 29,795 workers operating across multiple shifts, operating round the clock. The factory never stopped. As soon as one aircraft completed, the next began.
The B-29 program's total cost exceeded $3 billion in 1944 dollars, approximately $49 billion in current currency. This made it the most expensive military program of World War II, exceeding even the Manhattan Project's $1.9 billion budget. Per aircraft cost, each B-29 cost $639,188 in 1945, roughly $10.5 million today. For comparison, B-17 Flying Fortress, $238,329, B-24 Liberator, $215,516, P-51 Mustang Fighter, $50,985. The B-29 cost nearly 3 times more than contemporary heavy bombers and 12 times more than fighters. Why so expensive? Development costs. The complex systems required extensive research, testing, and refinement. Pressurization, remote fire control, and high-altitude propulsion demanded solving problems never encountered before. Tooling and facilities. 4 massive new factories, plus thousands of specialized tools, jigs, and fixtures designed specifically for B-29 production. Skilled labor. Training 90,000 direct manufacturing workers, plus 250,000 supplier employees. Materials. Specialized aluminum alloys, precision components, and electronic systems requiring expensive materials and manufacturing processes. Modifications. Constant engineering changes meant aircraft were built, flown to modification depots, extensively reworked, and then delivered to operational units. Some B-29s underwent 75 major modifications after leaving the factory. The expense was justified by strategic necessity. Only the B-29 could strike Japan from distant bases, flying missions impossible for any other bomber. The investment enabled strategic bombing campaigns that systematically destroyed Japanese industry and ultimately delivered atomic weapons, ending the war. But the expense shocked planners accustomed to simpler military procurement. One B-29 cost what 600 jeeps, 30 medium tanks, or 12 fighter aircraft cost.
Every Superfortress represented massive resource investment.
The 20th Air Force began B-29 operations against Japan from bases in China and India in June 1944. By November, Marianas-based B-29s struck Japanese home islands directly. The strategic impact was devastating. Japanese industry concentrated in cities vulnerable to incendiary bombing. B-29s flying from Saipan, Tinian, and Guam operated beyond range of most Japanese fighters. The bombers flew at altitudes Japanese defenses struggled to reach. Their pressurized cabins and long range allowed missions lasting 12 to 16 hours, impossible for crews in unpressurized aircraft. March 9–10, 1945, Operation Meeting House, 334 B-29s firebombed Tokyo, killing approximately 100,000 civilians and destroying 16 square miles of the city. It was the single most destructive bombing raid in history. July–August 1945, B-29s dropped atomic bombs on Hiroshima, August 6th, and Nagasaki, August 9th, delivering weapons that killed over 200,000 people and forced Japanese surrender. Between June 1944 and August 1945, B-29s flew approximately 34,000 sorties, dropped 170,000 tons of bombs, and destroyed major portions of Japan's 67 largest cities. The strategic bombing campaign, possible only because B-29s could reach Japan from bases 1,500 miles distant, contributed decisively to ending the war.
Japanese engineers studying B-29 wreckage from shot-down bombers reached devastating conclusions about their nation's industrial capacity. Every crashed B-29 was meticulously examined. Components were measured, materials analyzed, systems reverse-engineered as much as wreckage allowed. What Japanese engineers learned told them the war was lost. Complexity beyond Japanese capability. The analog fire control computers alone represented manufacturing precision Japan couldn't match. The electrical systems used components Japan didn't produce. The pressurization systems employed techniques Japanese engineers understood theoretically but had never implemented. Manufacturing scale. Each B-29 required 55,000 parts from 1,500 suppliers coordinated across 4 main assembly plants. Japanese industry couldn't organize production at such scale. Japan's dispersed, bomb-damaged factories struggled to maintain production of far simpler aircraft. Material quality. American aluminum alloys exceeded Japanese metallurgical capabilities. The Wright R-3350 engines used materials and manufacturing processes Japan couldn't duplicate. Cost implications. If each B-29 cost $639,188 and America had over 2,000 operational, the total investment exceeded $1.2 billion just for aircraft. Add bombs, fuel, bases, and training, the campaign cost more than Japan's entire war budget for multiple years. One Japanese engineer's report captured the hopelessness. To build one B-29 equivalent would require our entire aircraft industry's capacity for 6 months. America builds 4 daily from one factory. This war cannot be won through any effort we can muster.
The Soviet Tu-4 program demonstrated how difficult replicating a B-29 actually was. Soviet engineers had 3 complete examples. They could disassemble every component, measure it precisely, analyze every material, and copy systems exactly. Yet even with this overwhelming advantage, the first Tu-4 didn't fly until May 19, 1947, 3 years after capturing the B-29s.
The program required 900 factories contributing components, development of new aluminum alloys matching American specifications, creating manufacturing processes for precision components, training tens of thousands of workers in techniques they'd never encountered, and converting measurements from imperial to metric, which required redesigning many components because direct conversions produced impractical dimensions. The Wright R-3350 engines proved impossible to duplicate. Soviet industry couldn't manufacture them. Instead, Soviets developed the Shvetsov ASH-73TK radial, similar power output, but entirely new design requiring years of development. Total Tu-4 production, 847 aircraft built 1947 to 1952. The cost consumed resources the Soviet economy could barely afford. Stalin considered the program essential for nuclear deterrence. Soviet atomic weapons needed bombers to deliver them. The Tu-4 proved that even with complete examples to copy, building B-29 equivalent bombers required industrial capacity only superpowers possessed.
The B-29 Superfortress represented the pinnacle of piston-engine bomber design, so complex that even allies with captured examples required years to duplicate it. 55,000 parts, 600,000 rivets, 9 miles of wiring, analog computers, pressurization systems, remote gun turrets, 4 temperamental engines, a price tag exceeding the atomic bomb project. The complexity wasn't accidental. It emerged from strategic requirements. Strike Japan from bases beyond Japanese fighter range. Carry heavy bomb loads 3,000+ miles round trip. Operate at altitudes Japanese defenses couldn't reach. Protect crews during 12 to 16-hour missions. Meeting those requirements demanded technologies that didn't exist when design began. Boeing engineers invented pressurization systems, remote fire control, and high-altitude propulsion through systematic problem-solving backed by unlimited resources and urgent timelines. The $3 billion program shocked even American planners accustomed to massive military spending. But the investment paid strategic dividends. B-29s destroyed Japanese war industry, delivered atomic weapons, and ended the war months or years earlier than conventional invasion would have. Japanese engineers studying B-29 wreckage understood they couldn't compete. Soviet engineers with 3 intact examples needed 3 years to duplicate them. The complexity was deliberate, strategic, and ultimately decisive. Boeing Wichita's 1,644 B-29s, built by workers who had never seen such complexity, demonstrated that American industrial capacity could not just design revolutionary weapons, but mass-produce them faster than enemies could destroy them. German generals laughed at American car makers building tanks. Japanese generals dismissed American industrial capacity as inferior to Japanese discipline and fighting spirit. Soviet engineers thought they could quickly copy captured technology. All learned the same lesson. American industrial capacity, properly organized and motivated, could produce weapons of such complexity and in such quantities that competing became pointless. Not through superior tactics or battlefield genius, but through systematic application of mass production principles to military equipment that enemies considered impossible to manufacture at scale. 55,000 parts per bomber, 3,970 bombers total. More expensive than the atomic bomb they carried, more complex than anything else that flew during World War II. Built by car makers in Kansas, who proved that complexity, properly managed, could be mass-produced. In memory of the 90,000 workers who built B-29 Superfortresses, the air crews who flew them into combat, and all who understood that winning modern war requires not just courage, but industrial capacity to produce weapons enemies cannot match.